This is a fun demonstration I like to do to really reiterate how equilibrium can be the same rates, but different amounts of reactants and products. And so give this a try on your own. You can watch this video too instead, and I'll walk through it either way. But the idea is to start with a pile of reactants and kind of go step by step through a reaction. So these are things that are happening in, a fraction of the blink of an eye. But for us, we're just going to slow the process down and use objects to kind of get a sense of what dynamic equilibrium is. So we're going to start with just 40 objects. So we can think of each of these objects as a reactant, right? Like, so it's a chemical. And so I'm going to be using, I grabbed 40 little toys from my kids' playroom. Typically when we do this in the classroom, I bring in a bunch of candy and we find out who likes M&Ms more and who likes Skittles more. So I don't have any. So we're going to use little dragons and little animals. And I've got a pile of 40 of them right here. So I've got 40 of these all right here, and these are going to be labeled as reactants. And as my reaction progresses, some of these reactants, we're going to have, I've got a zombie and a red dragon. They're going to collide. And if they collide in the right orientation, they're going to turn into, and with the right energy, some sort of product, a hybrid zombie dragon. So that's a good product. And then they'll come and be set here in the product side. All right, so I have a few rules for this. I have 40 reactants to start with and 0 products. Now, for each step of my reaction, my rate of my reaction is going to be characterized as the transfer of half of the objects that are reactants to the product side. So my reactants are going to become products by half of them turning into products at each step. And my products are going to be able to turn into reactants. I'll have the reverse reaction occurring, but only a quarter of them will be able to turn into products. And we're just going to keep going until we think we hit dynamic equilibrium. So I have 40 to start with. I'm going to go ahead and move these each time, and I'm going to record these as we go. So as we look at this, we're going to move so I have an initial number of objects. I'm going to keep track on this of 40 reactants and 0 products. So for my first step, I'm going to transfer 20 objects of my reactants to my products and 0 to my reactants. And so what I'm doing here is I'm taking my initial and I'm multiplying it by 1/4. And on my reactant side, I'm multiplying it by 1/2. And that's the amount I'm going to transfer. And then I'm going to look at the outcome. So I'm going to take 20 of these over. So in that first step, I moved 20 of my reactants to my products, and I moved 0 products to reactants because I had 0 products. So that was our first step. So I'm just going to record that now that I've got these 2 piles made. So now at the end of that, I have 20 of my reactants around, and I have 20 of my products. So now I'm going to do another transfer. Now each transfer is going to be simultaneous. So I'm going to think about what's half of my 20. So that'll be 10. And a quarter of my 20 objects for my products will be 5. So I'm going to transfer these at the exact same time. So I'm going to pull these out. All right, I've separated out 5 of my products. I think I've got 10 there of my reactants. And now what I'm going to do, is swap them. Green instead of, all right, maybe that worked. Yeah, I got them. All right, cool. So now I've got a lot more products than I have reactants. And so what I end up with is, so I've lost 10 but gained 5. So I'll have 15 of my reactants, and I have gained 10 but lost 5. So I'll have 25 of my products. And then this will happen again. When I hit a point where I would have a fraction, I'm just going to round up for both of them. So my next transfer, I'm going to transfer half of my 15. So that'd be 7.5. So I'm going to round that up to 8. And it doesn't matter if I round up or round down, just as long as I do it consistently. A quarter of 25 is going to be 5 plus 1.25. So that's going to be, we'll just round that up to 6, even though it would round down. But we're just going to be consistent about always going up or always going down, regardless of if it's at a half or less than a half. Sorry, apparently math is hard. 5 plus 1.25 is 6.125. So I'm going to round up to 7. All right, so I've got my 8 transferring and then my 7. So I'm going to count those out. So I count them out on each side and then I swap them at the same time. So I've got 1, 2, 3, 4, 5, 6, 7, 8 of my reactants that I'm going to get rid of and 7 of my products. 1, 2, 3, 4, 5, 6, 7. All right, and I transfer these at the same time. All right, and then I can go through and count these and see how many I have. And when I do that, I'm going to see that I end up with 14 on my reactant side and 26 on my product side. And I'm going to do this again. So about half of 14 is at least a whole number this time. It's going to be 7 that I transfer. And then my products, a quarter of that is going to be rounded to 7 as well. So I'll transfer these. 1, 2, 3, 4, 5. I've got 7 reactants and 7 products, and I transfer them at the same time. Okay, and now I count up what I have on each side, and when I do that, I have 14 still, and I have 26 still. And now I can keep doing this, and it'll keep being the same values. And so the number of my reactants isn't going to change, i.e. the concentration. And the number of my products aren't going to change, which is the concentration of my products. And if I'm looking at the number that are transferring, so I'm always transferring half or a quarter every single time, but I can see that right here, when I'm transferring 7 objects each time, even though I'm following these 2 different rules, I'm seeing the same rate. And so at this point, the rate of my forward and reverse reaction have become the same, and my concentration isn't changing. And so I have reached dynamic equilibrium for children's toys. Fantastic. I can characterize this ratio. I can characterize this reaction of like a hodgepodge of small figurines. And the way that I would do that is I would look at the ratio of my reactants to my products. So I could start with a lot more or a lot less, but I'll always hit the same ratio at the end when my rates are the same. And so if I look at my, we have to have some sort of formalization. So we're always characterizing a ratio in the exact same way, but we'll always characterize it as the products divided by the reactants. And so we'll always, and we'll talk about this in the next lecture a lot, but let's just take a look at what it would be here. And so I'm just going to go with the number of objects for my concentration. And so that would be 26 divided by 14, which is going to give me 1.86 or about 2. So I'm going to, because I mean, we're talking about like dragons. I'm going to call it counting object. I'm just going to say we're going to round to 1 sig fig. I'm kind of making that up, but it seems pretty inaccurate to be doing a reaction in terms of dragons. So we're going to have this reaction coefficient, like this ratio of 2 that we can compare. All right, so that's dynamic equilibrium. Now let's look at what happens when changes occur. And this is going to essentially set us up for talking about Le Chatelier's principle later. And this is all just kind of a way to get familiar with an intuitive sense of this, what we're going to be learning in this chapter before we dive into the math of it, because I think we'll be a lot better at getting through that piece of it if we have a good conceptual understanding of what we're looking at. So let's make a change. So The next step of this is we are going to remove some of the products. So we have our same equilibrium, and I'm going to remove 6. 1, 2, 3, 4, 5, and 6. And I'm going to set them aside. So if we were in class, you'd get to eat the M&Ms or the Skittles, but whatever. All right, so I've removed 6. So remember where I was at equilibrium. So we'll just make a little note here. I had 14 of my reactants and I had 26. Then I removed 6 of my products. So now I've disturbed equilibrium. I'm no longer at it, right? So I'll have 14 and 20. And now I'm going to do my same process. I'm going to transfer a quarter from my products. I'm going to transfer half of my reactants. So that'll be 7. And a quarter of 20 is 5. So let's take these 1, 2, 3, 4, 5. All right. So I transfer 5 to my reactants and 7 to my products at the same time. And I'm going to end up with a value that is going to be 22 and 12. So I'll have 12 here and 22 here. All right, going to do the same thing. So in this time, half of my 12 is 6, and a quarter of my 22 is going to be, it's if I round up, so it's gonna be like 5.5, right? So I'm gonna round up to 6. So I'll transfer these 1, 2, 3. All right, so I've got 6 from each. And I'm transferring my piles and I'm going to count them up. So I'm going to count up my reactants and count up my products. And when I do that, I'm going to get a value that is, and you guessed it, 12 and 22. So we've hit equilibrium again. And that's because we can see that the number that I'm transferring back and forth, so that rate is the same. All right, so let's see if we're back at equilibrium, if we can characterize it in the same way. So let's look at our products over our reactants. So that's going to be 22 divided by 12, which is going to give me a value that is, in fact, pretty close to 2. It's going to be 1.83 this time, which we're going to round to 2. All right, so we basically hit equilibrium. Now our rates are different, right? Like transferring 6 is a lower rate than transferring 7. So my rate is lower, but it's the same in both directions. And the ratio of my products to reactants is the same too, even though we're talking about different quantities. And so we've reestablished equilibrium with the same ratio. So it's this ratio of the amount of products to the amount of reactants that will define equilibrium and be the same for a reaction no matter what you start with, which is cool, which is really cool. It's really exciting. It's, you know what it is? It's predictable. All right, let's do one more. I'm going to remove some of my reactants. So remember, I started with 12 and 22, and I'm going to, and we were at equilibrium, and now I'm going to disturb equilibrium. I'm going to remove 4. So now I'm going to have 8 of my reactants to start with and 22 of my products. So 1, 2, 3. All right, bye guys. Get rid of these. All right. So now what I'm going to do is do my same thing that I've been doing at the same rate. So I'm going to transfer half of my reactants. So that'll be 4, and a quarter of my products, sorry, which is going to be 6. That's 5.5, but we're going to round up. All right, I'm going to do that. All right, so I take 4 of my reactants and I take 6 of my products and I swap them. And now I count everything up. And when I do that, I'm going to see that I end up at 10 and I end up at 20. All right. So now I'm going to do this again. I'm going to transfer 5, which would be half of my reactants, and I'll transfer a quarter of my reactants, which will be 5. And when I do that, you can probably guess. All right, so I've got 5 of each, and I transfer them, and I count them up. I count up my piles, and I'm transferring the same number back and forth, right? So I'll have 10 and I'll have 20. Again, I'm at equilibrium. And that's because my rate of transfer, the amount going back and forth, this is the same. So let's try to characterize this as products over reactants and compare. This time I have 20 over 10, which is exactly 2 this time. So I'm getting the same ratio again and again, no matter how much I make changes, no matter what I start with. And that is the essence of dynamic equilibrium.